Welcome to today's STERIS Tech Talk on fundamentals of gamma irradiation. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Marute, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies, and I'll be the host for today's event. Our presenter today is Bryan Hardnacke, a Level 3 scientist at STERIS Applied Sterilization Technologies. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Bryan to begin the presentation.
Thank you. So today, learning about gamma radiation, we'll cover several things. We'll go over an introduction first. We'll talk about gamma technology overview, irradiator design and operation, how we qualify those irradiators, things we need to consider when we process products, applications, and technology comparison against other radiation services. So start with a background on what is radiation in the first place. Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. They can come from natural or artificial sources. So what you see here is the electromagnetic spectrum. It provides a classification of the entire range of the electromagnetic radiation according to wavelengths. Energy associated with the electromagnetic radiation is proportional to frequency and inversely proportional to wavelength. So electromagnetic waves with shorter wavelengths have more energy. You have, on the lower end, you would have radio waves, microwaves, infrared, and then towards the middle, visible light. And as we move towards more energetic, we have UV, X-ray, and gamma rays. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. Electromagnetic radiation can be further divided into ionizing and non-ionizing radiation. Anything below the UV spectrum is non-ionizing, whereas gamma, X-ray, and high ultraviolet light are ionizing radiation. Ionizing radiation has enough energy to detach electrons from atoms or molecules in the matter through which they pass, thereby ionizing the atom, causing some type of chemical reaction, such as the molecules within the cells of our body. There are a couple different types of radiation, beta, gamma, and X-ray. Gamma rays, or gamma radiation, it's a penetrating form of electromagnetic radiation that arises from the radioactive decay of atomic nuclei. These are the shortest wavelength of electromagnetic waves among the highest energy within the spectrum. Gamma rays are transmitted as photons. They are weightless packets of energy. Unlike alpha or beta particles, which have energy and mass, photons are pure energy with no mass, or essentially no mass and no charge. They do not interact strongly with matter because of this, because they don't have charge and essentially no mass, and that lets them penetrate deeper into most objects. They can travel further through air, obviously. They can penetrate barriers that would typically stop alpha and beta particles. Gamma can only be stopped by thick or dense enough layer of material with high atomic number, such as lead or depleted uranium being the most effective forms of shielding. There are a couple sources of gamma radiation that are typically used. Either cesium-137, cobalt-60 is the other main one. The main differences being cesium-37 produces gamma rays with a lower energy, has a much longer half-life. At STERIS facilities, you will see cobalt-60 in our irradiators for gamma processing. The reason we use that, cesium-137 is typically limited to small self-contained dry storage irradiators. They're used for radiation of blood or insect sterilization. Cesium-137 is a salt, so it can be soluble in water. That would complicate the safe handling of it. Whereas cobalt is a non-reactive metal, and in addition, it produces a higher energy gamma ray. So that lets it penetrate further than you would get with cesium-137 photons. So to actually produce cobalt-60, we start with natural cobalt. For cobalt, there's 100% abundance of the stable isotope cobalt-59 occurring naturally. So cobalt-60 is a man-made thing. Small slugs are placed into a nuclear power reactor where they stay for a limited period of time, sometimes 18 to 24 months, depending on the neutron flux at that location. While the slugs are in the reactor, the cobalt-59 atom absorbs a single neutron, and that makes it become cobalt-60. Over time, the ratio of cobalt-60 to cobalt-59 increases. Cobalt-60, because it doesn't occur naturally, is unstable because of that extra neutron. Therefore, it eventually emits 1 electron and 2 gamma rays at energies of 1.17 MeV and 1.33 MeV. These 2 gamma rays are what's responsible for your radiation processing from each of these decays. With every decay of cobalt-60 atom, the strength of radioactivity level of the cobalt-60 source is decreasing. So that's what we mean when we say half-life. After about 5.27 years, 50% of the source would be less powerful, would have less energy. And we lose about 12% on that source in a single year. In 50 years, 99.9% of cobalt-60 in a radiator would decay into inactive nickel-60. That would be returned to the supplier for reuse, recycling, or disposal after 20 years. So obviously, because it decays at that rate, we have to reload at given periods of time. It's important to note the energy needed to create cobalt-60 is much greater than the energy of the gamma rays emitted. The gamma rays emitted, therefore, are not energetic enough to activate product, but they can be used for other purposes, like sterilization or cross-linking, like we do at STERIS. So what does the actual source rack look like? So the cobalt-60 slugs that have been irradiated from cobalt-59, that's little number 1 right here. They're very small. They get put into a sealed alloy cylinder. It's typically 10 by 450 millimeters, and they get doubly encapsulated into a pencil. We call these pencils. The pencils get put in a certain array into a module. That's this little rectangle here. And then the module goes into the full source rack, which is typically 1 to 2 meters squared. So over here, you see an example of a source rack underwater. You see some of the pencils are lit up much brighter than other ones. Those are, they could be dummy pencils. So they are there to fill a space within the module. But they don't actually have enough source or enough radioactivity to be useful for processing. But they are important for how we want to arrange the source rack. So we would try to maximize the cobalt-60 irradiations. To the right side over here, you have pictures of a dummy pencil. Obviously, these are non-radioactive because we wouldn't be able to take a picture of it. Pencils are double encapsulated. So here you go is the slug, then a inner source element, and then the double encapsulation for the pencil. If you would compare it to a pencil with cobalt-60, outside of the source rack, just like above water, it would look the exact same, whether it's radioactive or not. There would be a temperature difference. The radioactive one would be much hotter. When you actually put the source rack underwater, we see Cherenkov radiation. That's that blue glow. That's the result of beta radiation traveling through water at faster than the speed of light. That's just a product of the cobalt-60 emissions interacting with the water that we use for shielding. So now we know what the source rack looks like. What does the actual irradiator look like? Some of the equipment needs to convey product safety to where cobalt-60 emission can deliver the required amount of energy to sterilize the product. So we have cobalt-60 in the source rack, which provides the photons for irradiation. We have the pencils, which we know are constructed from stainless steel. They hold the cobalt-60 with double encapsulation. The source rack moves up and down. That allows transfer of the pencils so that we can either irradiate them or safely store them. Customer product is loaded into carriers or on pallets. They're left on pallets. That lets them transport into the irradiator through the energy field and back out of the irradiator. So here you see a load unload station. It would come over this way through this maze. This is on the conveyance system. It would come around the source rack. Depending on the configuration, it might just make one pass or it might make several. Eventually it would come back out the other side and be unloaded. And we have various containment things to help us do this safely. Again, we have a pool of water. When the source rack is not in use, when we're not irradiating product, the source rack moves underwater. With concrete again. And there's a plug up here for whenever we have to reload source, because again, we do experience source decay, so that we have to replenish that every once in a while. And that gets plugged. We would drop the source in through there, they would load it up, and we would use it again. Irradiator sources can be in several different types of orientations. So here you see a rectangular source rack, which is most common for STERIS irradiators. And then here you see a cylindrical array. There are several different containers we can use to process product. So here you see carriers. These particular ones have false bottoms. So the load station would be up here. They would load the bottom level, and it gets lowered, load another level, it gets lowered all the way to the bottom. Then it goes through the irradiator. Here you see a smaller example of the same idea. It's another carrier, just much smaller. This is a pallet irradiator. So when we would receive a pallet straight from the customer, it would already have to be arranged a way we've agreed on based on PQ. We don't unpack it or anything. It would just go straight into the irradiator like that. Whereas with a carrier or totes, we have to actually unload the pallet and then reload it afterwards. And this is a carrier system, which is similar. I'm sorry, this is a tote. No, I'm sorry. This is a carrier. This is a tote. Carrier is hanging from the ceiling. It's the same idea. It's just moves differently. Some of the advantages, pallet system would be a little bit faster because we're not loading and unloading product. Whereas carriers and totes, we could maybe control the arrangement of product in there more, which might allow us to process a wider variety of products. But again, it would take more time. There is a potential to damage product if we're loading and unloading, which you don't see as much of that with the pallet irradiator. But again, the pallet has to be qualified as such, and we don't really have any options other than that. In terms of the operational modes, we'll get into this in a little bit more detail later, but it could be either a continuous system where we see one carrier or one tote go in at a time and one come out, or a batch system where all are in at once. They see every position in the irradiator and then they all come out at once. Conveyor path could take a couple different routes depending on the type of irradiator. It could have multiple passes, 1 to 2 levels. We'll discuss that further. For source rack design, there are a couple of things we need to consider in addition to exposure time. There are 3 main drivers that will affect dose delivery. Activity and distribution within the source rack. How hot is the source rack and where are those hot spots located? Distance of product from the source rack. Radiation follows the inverse square law. So dose received is inversely proportional to the distance from the source rack. So as your product passes through the irradiator, if it's a 4-pass irradiator, it'll get a much lower dose when it's further from the source, and you would expect all of, or the majority of the dose when it's passing closer to the source. And finally, attenuation due to product interactions or shielding. Consider the sun casting a tree shadow on the ground. The tree, which we can consider maybe another customer's product, it blocks the sun's radiation, the light and heat. The sun is analogous to the cobalt-60 source. It will block light and heat on certain parts of the ground, which will make those spots cooler. So other product in the irradiator can cast a gamma shadow, if you want to call it that, over product behind it in relation to the source rack during processing. And you can kind of visualize too, right? A leafier tree or a more dense tree would block more light or more radiation. So we really have to factor in product density variation as we process. There are 2 types of irradiation geometry: product overlap and source overlap. For source overlap irradiator, the height of the source rack is more than that of the product containers. So as you can see, it's not as efficient because we are losing cobalt. Whereas a product overlap irradiator, there are more passes around the irradiator. It has to go through each of these 4 levels or sides, whereas on this one, it would only have to go through 2. But then you're making more efficient use of your cobalt because you're capturing as much of that gamma radiation as you can. So a product overlap, for example, might have better overall dose uniformity within the product. And again, will intercept more of the radiation emitted from the source. But because you're removing 2 levels, there are transport mechanisms, so it makes it more complex mechanically. Attenuation due to product interactions. So depending on the number of passes, again, we have to consider customer product and the irradiator. Multiple passes can have transit or neighborhood effects on your product. So this is a JS8900 irradiator. It's only 2 passes. This is one we would use in batch mode. So you see a carrier, for example, would start in position 1, would go through all positions, and would be brought out of the irradiator if it was just a one pass, for example, all at the same time. For here, these are examples of a continuous irradiator, various continuous irradiators. Here you see another 2-pass one where a product would go in the irradiator and come out, one at a time, one in, one out. Same idea here with 4 passes. And this is a really common irradiator at a lot of our facilities. There's 8 passes on this one. So you see a product come in here, go up to this level, around, next to the source rack on the top level, back down, and then it would go across and do the same thing on the other side. And then again, one in, one out in that case. So as you can see, depending on the complexity of the irradiator path, there are a lot of shielding effects that must be considered. Density from customer product, or even partially loaded carriers or empty carriers. There are different ways to reduce the dose uniformity ratio, or DUR, in a product container. That's just the max dose divided by the min dose. That's a measure of how tight your dose range is, or how tight your processing is. If we were to irradiate just along one side of your product, say this is your source rack, you would see a dose curve similar to curve A here, where you would expect the max right here, and your min dose would be all the way on the other side of the product, which would make it very complicated. So that's why obviously we run this around the irradiator. It cycles around for another pass, and that the irradiator is on this side, the source rack's on this side. You'll get this dose curve. So where you see a max dose over here, min dose over here, dose is cumulative. So then your overall DUR, you would see max doses on the outside of the container, and you see a min dose towards the middle. It's a much tighter DUR, though, relationship between the min and max dose right here than you would see here. So this is why we have multi-pass irradiators. Again, same idea in a 4-pass irradiator. You can see how it gets hotter as it passes through, eventually getting all the radiation needed. So lateral dose variation may be reduced in several ways, either placing higher activity source pencils near the periphery of the source rack, or relative arrangement of product containers and the source. So source overlap or product overlap. The operational modes of processing. So we have continuous systems, incremental systems, and batch systems. For a continuous system, as we already saw a little bit, you would see one carrier go in, one carrier go out. It would hit, every pass. Incremental dose systems are different, whereas they complete laps around the source rack until processing requirements are met. So you can process products with different dose requirements together. As a product with a lower dose requirement completes processing, it can exit out of the radiation room, and other product in there would continue to complete laps. This is an automated process. So the planners would program in. We know, say we're getting 10 kilogray per lap. The customer requires 25 kilogray, so they need at least they need 3 complete laps around the source to meet their min dose. Again, a batch system. All product carriers are in the irradiator at the start of processing. These are a little bit more simple in that there's only one row of carriers on each side of the source, so we see less product interaction between carriers. And because of that, that allows for more precise dosing. But again, it might be more time consuming to get that set up. One thing that all these systems use is shuffle dwell. So carriers stay or dwell at designated irradiator positions around the radiation source for a certain dwell time, usually a few minutes. And then they move or shuffle to the next position such that each container eventually resides at each position before leaving the irradiator room. So if we have 28 positions in a continuous system, each carrier will see each of those 28 positions one time and then come out of the irradiator, whereas that could be more than once in an incremental system. Dwell time is selected based on the dose required by the customer. So when we qualify irradiators, it's dependent on a couple things. How are we designing? How has the irradiator been designed? What type of process load specifications are expected? What customer doses will we see? What are the dimensions, weight, and density of customer product? And the configuration of that. Can we process it on a pallet, or does it have to be unpalletized? Processing requirements. Do we want to be able to process with dissimilar products? Do we want to prioritize turnaround time? Do we want to minimize the effect of partially filled containers? These are all things we have to consider when we decide to qualify an irradiator. The first part of qualification would be IQ, installation qualification. Irradiator source rack and associated conveyor system are what's tested for this. There would be no dosimetry. That would essentially just be to make sure the mechanical aspects of the irradiator are performing as expected. The source rack goes to the expected position each time at the expected amount of time. And the conveyor system is traveling at the speed we expect. After that, we do operational qualification testing to determine that the irradiator is capable of operating and delivering appropriate doses. We use homogeneous material for that. So here you see an example of low-dose ethafoam homogeneous material, and this is either a mid-density or high-density homogeneous cardboard. We do several studies for OQ testing. There are transition studies, process interrupt, partially filled irradiation containers. We look for the routine monitoring locations, variability, timer setting and dose delivered, the dose linearity of our irradiator, and if there is off-carrier processing, we would also qualify that. We do this at defined intervals and following any change to the irradiator, like for example, a source replenishment, which usually happens once per year. After IQ and OQ have been completed, we have PQ. Information from dose mapping families is used to determine values for processing parameters. That leads to load specifications, which lead to consistent processing after the initial PQ. So we use either customer product or simulated surrogate product, which could be rejected material or some material of similar size or density that would be packed the same way as the actual customer product. And we would run that with the knowing the customer dose specifications and the product specifications, radiator qualifications, and the dosimetry system itself. Are we able to process this for this customer? And additionally, operational requirements. Will we be able to do this lead time versus efficiency? And will we be able to actually monitor this product at the appropriate locations? Unlike OQ, there is no need to repeat PQ as long as no changes occur. But this is a thing that would be assessed by the customer. So how do we monitor dose for PQ? In routine processing, we use dosimetry systems. Dosimeters are devices that undergo some type of physical transformation that is measurable after being exposed to ionizing radiation. Common ones that we use at STERIS, alanine. You see here, the alanine itself is this little dot right here. And this packaging labeled with barcodes to keep traceability. But this is what you're actually measuring. You're looking at, this is a amino acid that's bound in wax. When it's exposed to ionizing radiation, there's a change in the electron spin. So it gets shot with microwaves, and we measure the difference in electron spin to see what the dose of that product was. Down here you see Perspex, polymethyl methacrylate. This is a much more visible change. You'll see it actually darken when it's exposed to ionizing radiation. And then we would measure that in a spectrophotometer, which would measure the amount of light that passes through the dosimeter as a function of the thickness of the dosimeter. So what is gamma radiation used for? You see some example products down here. Medical devices, pharmaceuticals, active pharmaceutical ingredients, human animal tissue, implants, like knee or dental implants, labware, animal food or pet treats, food and spices, food packaging, cosmetics, botanicals. Why would you want to choose gamma processing for these products over a different type of processing? If your product has high strength, non-breathable materials, either the packaging or the raw product itself, gamma would be able to penetrate and irradiate all of the product. Again, irradiation of steam, gas, or electrons, and there are no unwanted chemical residuals involved in the gamma process. So a comparison of the industrial radiation processes we have at STERIS. I'll just focus on gamma. We use isotropic photons, average energy of 1.25 MeV. Typically, dose range achievable for medical device density would be 25 to 40 kilogray. Ideally, 25 to 50 kilogray is easier for us to process. We have a dose rate of a few kilogray per hour in gamma. The temperature of the irradiator depends on the design and how hot the source rack is. Typically, the maximum temperatures in a gamma radiator would go 45 to 50 degrees Celsius. So that would be a consideration as well. Thank you for calling in. I'll hand it back over.
Thanks again for joining us today. This concludes the webinar.